It's question 3 on the 2016 AS Physics Unit 1 paper, and question 3 is our stars question. So they're going to be utilising the three formulas: Wien's law, Stefan's law, and the inverse square law for intensity, and they do in fact utilise them all. To start with, this Wien's law, they give us a spectral intensity graph here for two stars, Sirius and Canopus, and they want us to confirm that Wien's displacement law works for these, right? They've given us the temperature. We can look at the maximum wavelength of spectral intensity on the graph and chuck it into Wien's law to show it works, right? So there's the law. It's in the formula booklet. I've rearranged it to give temperature is the Wien's constant over lambda max. So for Sirius, the Wien's constant is obviously in your formula booklet. Lambda max for Sirius, if you very, very carefully look at it, it's about 290. Don't forget this is in nanometers. Make sure you put the 10 to the minus 9. That's an easy mistake to make. Chuck that in the calculator. It comes out as 10,000 Kelvin, which is what it said. Happy days. Do the same for Canopus. If you look for the maximum spectral intensity wavelength, it's 400 nanometers. Don't forget the 10 to the minus 9. Chuck those numbers in your calculator and it comes out bang on 7250. Happy days. Right, on to the next bit. Astronomers state that one of the stars appears bluer than the other. Explain how the spectra supports this statement and which one is it. Right, now don't forget on your electromagnetic spectrum, bluish is 4ish to 500, reddish is 6ish to 700. Right, if I look at 400 odd there, this one has much higher spectral intensity at 400 nanometers. So Sirius A would appear bluer. So I've written Sirius would appear more blue as it has the greater spectral intensity at 400 nanometers, the blue end of the spectrum. And then the next bit, you know Stefan's law has come in, and you know that the inverse square law has probably come in. This is the Stefan's law part for 4 marks. They give us the radius of the two stars, and they want us to show that the luminosity of the one star is 500 times the luminosity of the other. So work out the two luminosities, divide them, and it should come out roughly 500. So luminosity or power, don't forget both of those words are effectively the same thing, is determined by Stefan's law. Surface area, the area is a sphere, 4 pi r squared, times Stefan's constant, 5.67 times 10 to the minus 8, multiplied by the surface temperature of the star to the power of 4. Do not forget that. Right? So chuck in the data we have for Canopus. 4 pi r squared is the radius of Canopus. Put it squared. Stefan's constant. The temperature, don't forget they gave us that on the graph, to the power 4. I got 4.9 times 10 to the 30 watts. Don't forget we're working out power, so the unit is watts. Do the same for Sirius. 4 pi r squared. There's the value for the radius. Stefan's constant. Surface temperature of the star. Again, they gave us that on the graph, to the power 4. Chuck it all in. I come out as 1 times 10 to the 28 watts. Now they wanted us to show that this one is about 500 times the size of this one. So if I divide those numbers, it comes out as 490, which is pretty blinking close to 500 as far as I am concerned. Happy days. Next part, calculate the intensity. Right, so you've got to think intensity. It's the inverse square law. It's the power of the star divided by 4 pi r squared, where r, I've called it d here to remember, it's the distance between the two stars that you are looking at. Calculate the intensity of the radiation reaching Earth from Sirius A, and they give us the distance between Earth and Sirius A. So that's what we'll put in there for that 4 pi r squared. Think of r as the distance between them. We calculated the power or luminosity of the radiation coming from Sirius A in the previous question. 1 times 10 to the 28. Chuck it all in. Do it twice in case you press a wrong button. And I've come out with 1.19 times 10 to the minus 7 watts per square meter. Alright, make sure you understand those units. Power is watts. and we're dividing by a distance squared, right? So meters to the minus 2. Last bit, the intensity of the radiation reaching Earth's surface from the other star Canopus is less than that from Sirius, even though the power of Canopus, look, was 500 times bigger. Explain this apparent contradiction. Well, the most obvious thing is that Canopus is much, much further away from the Earth than the Sirius star. And as it is an inverse square law, right, because the intensity is inversely proportional to that distance squared, is spread out over much a greater surface area. Okay, I've got to be honest, that was a pretty good stars question. Hope you enjoyed it. 13 marks. See you at the next one.